On July 1st, 2025, a telescope in Chile detected something moving wrong. Not a comet on a familiar orbit. Not an asteroid circling our sun. This object came from outside, from the darkness between stars, traveling at over 130,000 miles per hour through our solar system. They named it 3I Atlas, the third interstellar visitor ever confirmed in human history. But 3I Atlas isn't like the others. It's 1,000 times more massive than it should be. Its chemical composition doesn't match any comet we've studied. It produced a narrow jet pointing toward the sun, something comets aren't supposed to do. Its trajectory aligned suspiciously with the plane where our planets orbit, passing close to Mars, as if it were surveying our system. And then there's the metal, nickel detected in its coma, nickel without iron. A combination that resembles industrial refinement more than natural formation. Most scientists say it's just an unusual comet, rare but natural. Some aren't so sure, because 3I Atlas has too many anomalies, too many coincidences, and it's already leaving, fading back into interstellar space, taking its secrets with it. So what if it wasn't natural? What if something built it? What if we just watched an alien probe pass through our solar system and barely noticed? Tonight, we'll examine every anomaly. We'll analyze the data scientists don't want to talk about. We'll explore the possibility that's been dismissed too quickly. And we'll ask the question that keeps astronomers awake. Could 3I Atlas be the first confirmed artificial object from another civilization? This is the story of 3I Atlas, and the question nobody wants to answer. But before we begin, if you'd like to support the channel, please take a moment to like and subscribe. I can't thank you enough for your support. And also, I'd love to know where you're tuning from and what time it is there. It makes me so happy to see how these videos connect people from around the world. Now, settle in and let's dive in. Let's start with what we know for certain. 3I Atlas was first observed on July 1st, 2025, by a remote telescope in Chile, part of the Atlas network designed to detect potentially hazardous asteroids. Initial observations showed an object with a hyperbolic trajectory, meaning its path through space was open-ended, not bound to our sun's gravity. This is the signature of an interstellar origin. Objects born in our solar system follow elliptical orbits, returning again and again in predictable cycles. Interstellar objects come from elsewhere, swing past our sun once and then leave forever, disappearing back into the cosmic void. The confirmation came quickly. Archives were searched, pre-discovery images were found, frames captured by Atlas telescopes around the world and by the Zwicky Transient Facility in California. Images taken before anyone knew what they were looking at. These early observations pushed the discovery date back, giving astronomers precious additional data points to calculate the object's trajectory with greater precision. And that trajectory told a story. 3I Atlas entered our solar system from interstellar space, traveling inward toward the sun. By early October 2025, it passed within approximately 30 million kilometers of Mars, close enough for spacecraft orbiting the red planet to observe it. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter both turned their cameras and spectrometers toward this visitor, capturing data about its composition and behavior. On October 29, 2025, 3I Atlas reached perihelion, its closest approach to the Sun, before beginning its long journey outward, back toward interstellar space. At no point did 3I Atlas pose any threat to Earth. Its closest approach to our planet was approximately 1.8 astronomical units, about 270 million kilometers, well beyond even the orbit of Mars. You were safe. We were all safe. But safety isn't what makes this object fascinating. What makes 3I Atlas fascinating are the anomalies. Let's talk about size. When astronomers first calculated the dimensions of 3I Atlas, something didn't add up. The object appeared to have a diameter larger than 5 kilometers, potentially much larger. Now, 5 kilometers might not sound enormous. It's about 3 miles across. You could walk around it in an afternoon, assuming you had a spacesuit and a very unusual afternoon planned. But here's the problem. That makes 3I Atlas vastly larger than the other interstellar objects we've observed. Oumuamua, the first interstellar visitor, was estimated to be somewhere between 100 and 400 meters in length, roughly the size of a large building or a small mountain, depending on its exact dimensions. Comet 2I Borisov had a nucleus estimated at around 400 meters to possibly 1 kilometer across. Comets, in general, tend to be relatively small objects, dirty snowballs as they're sometimes called, made of ice and rock and dust. 3I Atlas, with a minimum diameter of 5 kilometers, is potentially 5 to 50 times larger than these previous visitors. That's not a small difference. That's an order of magnitude difference. That's the difference between a house and a city block, between a pond and a lake. But size alone isn't the real anomaly. Size is just the beginning. The real anomaly is mass. In September 2025, researchers published an analysis examining the trajectory of 3I Atlas with extreme precision, looking for something called non-gravitational acceleration. Now, this is important, so let's break it down. When a comet approaches the Sun, solar radiation heats its surface. Ices sublimate. They turn directly from solid to gas without becoming liquid first. This creates jets of gas and dust that stream away from the comet's surface. Those jets create thrust, tiny but measurable. This thrust causes the comet's trajectory to deviate slightly from what pure gravitational forces would predict. Astronomers call this non-gravitational acceleration, and it's a standard feature of cometary behavior. Here's what's strange. Between May 15th and September 23rd, 2025, researchers found that 3I Atlas showed no measurable non-gravitational acceleration. Zero. Despite the fact that the object was clearly active, it was producing a visible coma, that fuzzy cloud of gas and dust that surrounds an active comet. Its trajectory remained purely gravitational. This should be impossible, or rather, it should be extremely unlikely. The only way a comet can outgas without experiencing non-gravitational acceleration is if the mass of the nucleus is so large that the thrust from the jets becomes negligible, like trying to push a mountain with a garden hose. The jets are there, but they're not strong enough to noticeably alter the trajectory of something so massive. Running the numbers, researchers concluded that for 3I Atlas to show no non-gravitational acceleration, despite its observed activity, its mass must exceed 33 billion tons. 33 billion tons. That's 33,000 kilograms. That's roughly equivalent to the mass of a small metallic asteroid, not a fluffy comet made of ice and dust. To put this in perspective, 33 billion tons is approximately 1,000 to 1 million times more massive than the estimated masses of Oumuamua and Comet 2I Borisov. 1,000 to 1 million times. This isn't just larger, this is anomalously massive, in the words of the researchers themselves. Think about that for a moment. The third interstellar object ever observed isn't just bigger than the first two. It's so much more massive that it exists in a completely different category. It's like comparing a bicycle to a freight train. Both are vehicles, technically, but they operate on entirely different scales. Now here's where it gets strange. If 3I Atlas is truly this massive, what is it made of? Comets are typically composed of water ice, frozen carbon dioxide, frozen carbon monoxide, and various rocky and dusty materials. These are relatively low-density materials. To pack 33 billion tons into an object with a diameter of only 5 kilometers or so, you would need an average density approaching or exceeding that of solid rock, or possibly even metal. But comets aren't supposed to be made of solid rock or metal. They're supposed to be porous, fluffy aggregates of ice and dust held together loosely by their own weak gravity. They're dirty snowballs, not dense boulders. The typical density of a comet nucleus is somewhere around 0.6 grams per cubic centimeter, about half the density of water ice. Yet the implied density of 3I Atlas, given its mass and estimated size, would need to be significantly higher, possibly 2, 3, even 4 times the typical cometary density. That's anomaly number 1. The mass doesn't match the object type. In August and September 2025, multiple observatories trained their spectrometers on 3I Atlas. Spectrometry is one of the most powerful tools in astronomy. By analyzing the wavelengths of light absorbed and emitted by an object, scientists can determine its chemical composition with remarkable precision. It's like reading a fingerprint, except the fingerprint tells you what something is made of, down to the molecular level. The spectrometric data from 3I Atlas revealed a composition that was unusual. According to observations, particularly from the James Webb Space Telescope, the coma of 3I Atlas, the cloud of gas surrounding the nucleus, was composed primarily of carbon dioxide, approximately 87% by mass. Carbon monoxide made up about 9%. Water constituted most of the remaining 4%, with trace amounts of cyanide compounds also detected. Now, carbon dioxide-dominated comets aren't unheard of. They exist. We've seen them before. But they're relatively rare. Most comets in our solar system are water-dominated. Water ice is the primary volatile material, with carbon dioxide and carbon monoxide as secondary components. Finding a comet that is primarily carbon dioxide, with water as only a minor constituent, suggests formation in a very cold environment, colder than the regions where most solar system comets formed. This makes sense for an interstellar object. 3I Atlas formed in another solar system, possibly in a region much colder than our own outer solar system. Different stellar systems have different chemical compositions, different temperature gradients, different formation histories. An alien comet, born light years away under different conditions, would naturally have a different composition than our native comets. But then there's the metal. Spectroscopic observations detected nickel in the coma of 3I Atlas. Nickel, a metallic element. Now, finding trace metals in comets isn't unprecedented. Comets can contain various elements, including metals, as part of their rocky dust component. But the presence of nickel, and specifically nickel without a corresponding detection of iron, raised eyebrows. Why? Because in nature, nickel and iron almost always occur together. They're chemically similar. They're often found in the same minerals, in the same meteorites, in the same planetary cores. When asteroids differentiate, when they melt and separate into layers based on density, iron and nickel sink together to form metallic cores. When supernovae explode and forge heavy elements, they create iron and nickel in similar abundances. The universe, in general, doesn't separate nickel from iron, except, apparently, in 3I Atlas. One researcher noted that finding nickel without iron is unusual because it resembles industrial production methods. On Earth, we refine nickel and separate it from iron for specific technological applications. High-purity nickel alloys are used in specialized equipment, in electronics, in aerospace engineering. But nature doesn't typically refine metals. Nature mixes them. Now, let's be absolutely clear. The absence of detected iron doesn't necessarily mean iron isn't there. Spectroscopy has limitations. Detection depends on what elements are being released into the coma, which depends on temperature, sublimation rates, and local chemistry. It's entirely possible that iron is present in 3I Atlas, but simply wasn't vaporized in sufficient quantities to be detected. Or it was present, but in forms that didn't produce clear spectral lines. But still, the detection of nickel without iron is unusual. Not impossible, not definitive proof of anything, but unusual. This is anomaly number 2, a chemical composition that doesn't quite fit standard cometry models. In July 2025, the Hubble Space Telescope captured an image of 3I Atlas that caught everyone's attention. The image showed a narrow, forward-pointing jet extending from the nucleus toward the Sun. This jet was approximately 10 times longer than it was wide, a thin, directed stream of material rather than a broad, diffuse plume. And critically, it was pointing toward the Sun, not away from it. Let's pause here. This is important. When most people think about comets, they picture a bright head with a long tail streaming behind, pointing away from the Sun. That's the classic image. A comet's tail always points away from the Sun because it's pushed by solar radiation pressure and the solar wind. Sunlight physically shoves dust particles outward. The solar wind, a stream of charged particles flowing from the Sun, pushes ionized gas outward. The tail is the debris trail left behind as the comet races through space. But 3i Atlas showed a forward jet, a jet pointing toward the sun. Now, forward jets are not unknown in cometary science. They can occur when volatile ices on the sunward side of a rotating nucleus sublimate preferentially, creating thrust that propels material forward. The comet rotates, different regions face the sun, outgassing patterns change. Under certain conditions, jets can point in various directions, including forward. But a forward jet that is 10 times longer than it is wide? That's unusual. That suggests a highly collimated, focused stream of material, almost like the exhaust from a nozzle. Natural sublimation typically creates broader, more diffuse plumes, and less confined by topography like a crater or a fissure. Here's where things get interesting. Focused jets require specific geometric conditions. You need vents, valleys, depressions, structures that channel escaping gas in particular directions. Random ice sublimation across a surface creates a more or less spherical coma. Directed jets require directed structures, and structures imply geology, specific shapes, specific configurations. Could 3i Atlas have such structures? Absolutely. Comets can be geologically complex. They can have craters, cliffs, valleys, smooth plains, rugged terrain. We've sent spacecraft to comets before. We've seen their surfaces up close. They're not featureless snowballs, they're worlds, small and strange, but worlds nonetheless. But we haven't seen the surface of 3i Atlas. We can't. It's too far away. Too small. Even Hubble can't resolve surface features at that distance. We see only the coma, the jets, the overall glow. The nucleus itself remains hidden beneath its own cloud. So we're left with an observation, a narrow, forward-pointing jet, unlike the broad tails typically associated with comets. Not impossible, not beyond natural explanation, but another piece in a growing puzzle. Anomaly number 3. Unusual outgassing geometry. Now let's talk about where 3i Atlas came from, and more importantly, where it's going. Interstellar space is vast, unimaginably vast. The distance to the nearest star system, Proxima Centauri, is about 4.24 light-years. That's roughly 40 trillion kilometers. Space is so empty that the average density of matter in the interstellar medium is about 1 atom per cubic centimeter. You could fit billions of atoms in a grain of sand. Space has 1 atom per cubic centimeter. In this vast emptiness, interstellar objects drift. They're ejected from their birth systems, tossed out by gravitational interactions with planets, stars, or other objects, and then coast through the void for millions or billions of years. They move in essentially straight lines, their trajectories determined by their initial ejection velocity and perturbed only slightly by the distant gravity of stars they pass. The probability of an interstellar object randomly encountering another star system is infinitesimally small. Space is too big. Stars are too far apart. Most interstellar objects will drift forever, never coming close to another star, never being observed by anyone anywhere. Yet 3 Atlas not only entered our solar system, a statistical rarity in itself, but it did so on a trajectory that brought it unusually close to multiple planets. Here's what we know. 3i Atlas passed within about 30 million kilometers of Mars in early October 2025. That's close. Not dangerously close, but close enough that spacecraft orbiting Mars could observe it in detail. The object also passed relatively close to Jupiter during its inbound journey, though exact distance figures for Jupiter vary depending on timing and observation windows. Now, passing near planets isn't necessarily suspicious. Our solar system is full of planets, and any object moving through the inner system has a decent chance of passing relatively near at least one. But here's the thing. 3i Atlas's trajectory is closely aligned with the solar system's ecliptic plane. The ecliptic plane is the flat disk that contains the orbits of the planets: Earth, Mars, Venus, Jupiter, Saturn. They all orbit the Sun in roughly the same plane, give or take a few degrees. This alignment exists, because the solar system formed from a rotating disk of gas and dust. Everything settled into that disk, and the planets coalesced there. Interstellar objects, however, should arrive from random directions. Space has no preferred orientation. An object ejected from a distant star system could come from any direction, from above the ecliptic, from below, from the side, at any angle. There's no reason for interstellar visitors to preferentially arrive along the plane of our solar system. Yet 3I Atlas's trajectory is roughly aligned with the ecliptic. It entered the solar system at a relatively low inclination angle, meaning its path doesn't deviate dramatically from the plane where the planets orbit. Researchers have noted this alignment. Some have calculated the probability of a random interstellar object arriving with such an ecliptic-aligned trajectory. The exact numbers depend on assumptions about the distribution of interstellar object orbits, but the general consensus is that ecliptic alignment is less probable than a random orientation. Does this mean 3I Atlas's trajectory is impossible naturally? No, absolutely not. Statistics deals in probabilities, not impossibilities. Low probability events happen. They have to happen. If you roll a die enough times, you'll eventually get 10 sixes in a row, even though each individual occurrence has low odds. But low probability doesn't mean you ignore it. Low probability means you pay attention. Anomaly number 4, a trajectory that statistically favors passing near multiple planets in our solar system. At this point, you might be wondering, what do scientists think about all this? The answer is complicated and carefully worded. The scientific community has approached 3I Atlas with the same rigorous methodology applied to any astronomical object. Observations have been made, data has been collected. Models have been constructed, papers have been written, peer review is ongoing. Telescopes around the world and in orbit continue to track the object, gathering photometry, spectrometry, polarimetry, and imaging data. Official statements from space agencies emphasize the scientific value of 3I Atlas. NASA describes it as a rare opportunity to study an interstellar comet, to learn about the composition and characteristics of objects formed in other stellar systems. The European Space Agency coordinated observations from Mars orbit, using instruments originally designed to study the Martian surface, to instead examine this distant visitor. Universities and observatories globally have published findings on the object's light curve, rotation, outgassing behavior, and chemical composition. All of this is true. All of this is important science. Interstellar objects are incredibly valuable for understanding planetary formation, stellar system evolution, and the chemical diversity of the galaxy. Every new data point about 3I Atlas tells us something about the universe beyond our solar system. But there's also been another conversation, a quieter one, a more speculative one. Some researchers have published papers and articles raising questions about whether 3I Atlas could be something other than a natural comet. These papers don't claim definitive proof of anything artificial. They don't say, this is alien technology. What they say is, here are anomalies that don't easily fit standard models. Here are characteristics that warrant further investigation. Here are possibilities we should consider. This is important to understand. Science doesn't work in absolutes. Science works in hypotheses, evidence, probability, and uncertainty. When a scientist says, this could be X, they don't mean, this is X. They mean, X is a hypothesis worth testing. They mean, the data is consistent with X, among other explanations. So when papers are published, suggesting that 3I Atlas could potentially be an artificial object, what they're really saying is, the anomalies are significant enough that we shouldn't dismiss unconventional explanations without investigation. They're saying, extraordinary claims require extraordinary evidence, but extraordinary observations also deserve extraordinary attention. Other researchers have pushed back, and rightly so. They've pointed out that comets are diverse, that our models of cometary behavior are still incomplete, that we've only observed a handful of comets up close and thousands more only from a distance, that 3I Atlas, while unusual, isn't necessarily beyond the range of natural variation. That speculation without conclusive evidence can mislead the public and misrepresent scientific uncertainty. Both perspectives are valid. Both are necessary. Science advances through the tension between speculation and skepticism, between the willingness to consider new ideas and the insistence on rigorous proof. But here's what's undeniable. 3I Atlas has multiple characteristics that are individually unusual and collectively puzzling. Large size, anomalous mass, unusual composition, forward jet, ecliptic-aligned trajectory. Each individual anomaly has potential natural explanations, but taken together, they form a pattern that scientists are struggling to fit into standard cometry models. And so the observations continue. Telescopes track, data accumulates, models are refined, and the question remains unresolved. Let's engage in a thought experiment. Not a claim, not a conclusion, a thought experiment. What if 3I Atlas were not natural? What if, just as a hypothetical exercise, it were an artificial object, a probe, a spacecraft, something constructed by intelligent beings in another solar system and sent into the galaxy for reasons we can't fathom? What would such an object look like? First, it would need to survive interstellar space. The journey between stars takes millions of years, even at high velocities. Cosmic radiation is relentless. Interstellar dust, though sparse, impacts at enormous speeds. Micrometeorites erode surfaces. Any artificial interstellar probe would need to be durable, robust, probably heavily shielded. One way to shield a spacecraft is to encase it in something natural, something that blends in, something that looks like a comet. Comets are mostly ice and dust, low value, ignored by most survey telescopes. If you wanted to send a probe through a star system unnoticed, disguising it as a comet would be clever. Comets are expected. They're catalogued and then forgotten. Nobody investigates them deeply unless they're spectacular or threatening. A coating of ice and dust would also provide radiation shielding. It would protect internal systems from cosmic rays and solar radiation, and as the object approached a star, the ice would sublimate naturally, creating a coma and tail, exactly what you'd expect from a comet. But beneath that shell, there could be something else, something dense, something metallic. This would explain the anomalous mass. A rocky or metallic core beneath a relatively thin icy mantle could easily produce the observed mass-to-size ratio. The nucleus wouldn't be a fluffy aggregate. It would be a solid, heavy object, possibly a construct of refined metals and engineered materials, wrapped in a thin disguise of natural materials. This would also explain the unusual composition. If the icy shell is thin, and the underlying object is metallic or rocky, then the outgassing would reflect the composition of that shell, primarily carbon dioxide perhaps. If the outer coating formed in an extremely cold region or was intentionally composed of CO2 ice for stability. The detection of nickel without iron could represent alloy components of an internal structure. Materials chosen for strength or conductivity, leaking through cracks or vents in the coating. The forward jet. That's interesting. A highly collimated jet suggests a directed release of material. If there were internal chambers or vents, structures designed to vent gas in specific directions, perhaps for maneuvering or temperature regulation, then you'd see narrow jets rather than broad, symmetric outgassing. And the trajectory? This is perhaps the most intriguing point. If 3I Atlas were an artificial probe, its trajectory wouldn't be random. It would be planned. An interstellar probe would need to maximize scientific return, to observe as much of a star system as possible during its brief passage. Aligning with the ecliptic plane makes sense. That's where the planets are. That's where interesting things happen. A probe designed to survey our solar system would logically choose a path that brings it near multiple planets, allowing onboard instruments to gather data on Mars, perhaps Jupiter, perhaps Earth from a distance. Could you engineer such a trajectory? Yes, absolutely. Interstellar travel isn't magic. It's orbital mechanics on a very large scale. If a civilization could build an interstellar probe, already a colossal technological achievement, then calculating a trajectory that threads through a target star system's ecliptic plane would be straightforward. Difficult, but straightforward. You'd launch your probe with a precise velocity and direction. Millions of years later, it enters the target system, coasts through the habitable zone and inner system, gather data, and exit back into interstellar space. The probe doesn't stop. It doesn't orbit. It makes one pass and leaves. Fast, efficient, minimally invasive. From the perspective of anyone in the target system, it looks like a comet. Just another wanderer from the depths of space, unless someone looks closely, unless someone notices the anomalies. Here's the problem with the thought experiment. It's just a thought experiment. Everything described above is plausible in the sense that it doesn't violate known physics. But plausibility is not evidence. The fact that something could be true doesn't mean it is true. The universe is full of things that are merely possible, but not actual. Let's be clear about what we don't have. We don't have resolved images of the nucleus of 3I Atlas. We can't see its surface. We don't know its exact shape. We can't confirm whether it has structures, craters, facets, or anything else. All observations have been of the coma, the gas and dust surrounding the nucleus, not the nucleus itself. We don't have detailed compositional analysis of the nucleus material. Spectroscopy tells us what's in the coma, the gases being released, but the nucleus itself could be made of entirely different materials. The coma is the exhaust, not the engine. We don't have any signals, no radio transmissions, no laser pulses, no modulation patterns in reflected light, no communication of any kind. If 3I Atlas were a probe, it's either not trying to communicate, unable to communicate, or communicating in ways we can't detect. We don't have evidence of controlled maneuvers. The trajectory is consistent with gravitational motion. There's no sign of course corrections, deceleration, or intentional targeting beyond what could be explained by natural orbital mechanics and random chance. In short, we have anomalies, interesting anomalies, statistically unusual anomalies. But anomalies alone are not proof of artificiality. Nature is full of outliers. The universe is weird. Strange things happen naturally all the time without requiring intelligent intervention. Consider Oumuamua, the first interstellar object. It also had anomalies. It was highly elongated, shaped like a cigar or a pancake, depending on interpretation. It exhibited non-gravitational acceleration despite showing no visible coma, which led to speculation about everything from hydrogen icebergs to light sails. Some researchers proposed that Oumuamua could be an artificial object, perhaps a defunct probe tumbling through space. But over time, as more data was collected and models were refined, natural explanations emerged. Perhaps Oumuamua was a fragment of a larger body, broken apart by tidal forces or collision. Perhaps it was outgassing hydrogen or some other substance not easily detected. Perhaps its shape was the result of specific formation conditions in its birth system. None of these explanations are perfect, but they're plausible. And in the absence of extraordinary evidence, plausible natural explanations are preferred. The same principle applies to 3I Atlas. Yes, it's unusual. Yes, it has characteristics that challenge standard models. But challenging models is not the same as breaking physics. Science is constantly updating its models as new data arrives. Comets are more diverse than we thought. Chemical compositions vary more than expected. Trajectories occasionally align by chance. Anomalies get explained. That's what science does. It finds patterns, builds models, makes predictions, encounters exceptions, and refines the models. Repeat forever. And yet there's something about 3I Atlas that nags at the mind. Something about the accumulation of oddities. The size, the mass, the composition, the jet, the trajectory. Each one explainable maybe. But altogether, it's like finding a rock on a beach that's shaped exactly like a perfect cube. Sure, erosion could theoretically produce that shape. Random processes could, by chance, create sharp edges and flat faces. It's not impossible. But you'd still pick up the rock and look at it closely. You'd turn it over in your hands. You'd wonder, 3I Atlas is that rock, and we're still picking it up, still looking at it, still wondering. Let's talk about numbers. Cold, hard, uncomfortable numbers. Astronomers estimate that an interstellar object similar to Oumuamua passes through the inner solar system about once per year, though most are too faint to detect with current technology. Survey telescopes have only recently become powerful enough to spot these dim, fast-moving visitors. We're essentially standing in a dark room that's occasionally crossed by fireflies, and we've just now turned on a flashlight bright enough to see a few of them. But here's what's interesting. We've detected 3 interstellar objects in 8 years. 3 confirmed visitors: Oumuamua in 2017, 2I Borisov in 2019, 3I Atlas in 2025. That's a detection rate of roughly 1 every 2 to 3 years, given our current observational capabilities. Now, detection depends on many factors. Size matters. Larger objects reflect more light and are easier to spot. Trajectory matters. Objects passing closer to Earth are more visible than those remaining in the outer system. Timing matters. We can only observe objects when they're illuminated by the sun and positioned where telescopes can see them. Brightness matters. Some objects are more reflective than others. Given these limitations, the true population of interstellar objects passing through our solar system is certainly much higher than the number we detect. Perhaps hundreds per year, perhaps thousands. They come and go unseen, too small or too distant or too dark to register on our instruments. But of the 3 we have detected, 3I Atlas is by far the largest and most massive. By orders of magnitude. This is statistically peculiar. You would expect the first few interstellar objects discovered to be representative of the population as a whole, a mix of sizes, compositions, and characteristics. Yet 3I Atlas stands apart. It's an outlier among outliers. Think of it this way. If you're fishing in a lake and catch 3 fish and 2 are normal-sized bass, but the third is 100 times heavier than the other 2, you don't just shrug and assume that's typical. You start wondering if something unusual is going on. Maybe there's a different species in the lake. Maybe there's contamination affecting growth rates. Maybe someone stocked the lake with something that doesn't belong. 3I Atlas is that third fish. And it makes you wonder, are we catching what's actually out there, or are we catching what wants to be caught? There's something else about 3I Atlas that deserves attention. Something that hasn't been widely discussed in public discourse, but appears in technical papers and observatory reports. The object is travelling through our solar system at roughly 130,000 miles per hour, or approximately 210,000 kilometers per hour. Now, this is fast, very fast by human standards, but it's actually on the slower end for interstellar objects. Here's why that matters. Interstellar space is defined by velocity. Objects orbiting within our solar system have velocities relative to the Sun, ranging from a few kilometers per second for distant objects to tens of kilometers per second for inner system bodies. But to escape the Sun's gravity entirely, to become truly interstellar, you need to exceed escape velocity, which depends on your distance from the Sun. At Earth's orbital distance, solar escape velocity is about 42 kilometers per second. Interstellar objects arrive with velocities that reflect their journey through the galaxy. They've been accelerated by the gravity of their parent star, possibly perturbed by planets or other objects during ejection, and then coasted through interstellar space. By the time they enter another star system, they typically have velocities of 20 to 40 kilometers per second relative to that star, sometimes more, sometimes less. 3I Atlas, at roughly 58 kilometers per second, is moving fast but not exceptionally so. It's within the expected range for natural interstellar objects. Oumuamua, for comparison, had a solar system escape velocity of about 26 kilometers per second. 2I Borisov was moving at around 32 kilometers per second. But here's the interesting part. Velocity correlates with trajectory. Faster objects spend less time in the solar system. They sweep through quickly, interact briefly, and leave. Slower objects linger longer, allowing more time for observation and gravitational interactions with planets. 3I Atlas's velocity meant it was observable for several months. Not years, but months. Long enough for telescopes around the world to coordinate observations. Long enough for spacecraft at Mars to turn their instruments toward it. long enough for detailed spectrometry, photometry, and trajectory analysis. If you were designing an interstellar probe, you would need to balance speed with observation time. Too fast, and you don't gather enough data during your passage through the target system. Too slow, and you expend unnecessary energy. And your mission duration becomes prohibitively long. An optimal speed would allow a relatively quick transit, decades or centuries rather than millennia, while still providing sufficient time in the inner system to observe planets, measure stellar characteristics, and collect environmental data. 3i Atlas's velocity is in that optimal range. Not proof of anything, just optimal. When Oumuamua was discovered, a major SETI initiative pointed the Green Bank telescope in West Virginia toward the object, observing it for 6 hours across 4 radio frequency bands. They were looking for any sign of artificial transmission, radio signals, modulated emissions, anything that might indicate technology rather than nature. They found nothing. Silence. Oumuamua was radio quiet across all monitored frequencies. Similar observations were conducted for 2i Borisov. Again, nothing. No signals, no transmissions. Just the natural electromagnetic noise expected from a comet outgassing in sunlight. For 3i Atlas, radio observations were conducted by multiple facilities. The details of these observations haven't been widely publicized, but the general results are consistent. No detected artificial signals, no radio transmissions, no laser pulses, no modulated light patterns. Does this mean 3i Atlas isn't artificial? Not necessarily. The absence of detected signals doesn't prove the absence of technology. Consider these possibilities. First, the object might not be transmitting. If 3i Atlas were a probe, it might be passive, designed to observe and record rather than broadcast. There's no particular reason an interstellar probe would announce its presence. Stealth might be preferred, either for scientific non-interference or for security. A civilization capable of sending probes across light years might value discretion. Second, the object might be transmitting in ways we can't detect. Our radio searches cover specific frequency ranges, specific modulation types, specific signal characteristics. But there are infinite possible communication methods. Laser communications in optical or infrared frequencies, neutrino beams, gravitational wave modulation, quantum entanglement signaling. Some of these are speculative or beyond our current physics, but the point remains, we're searching for what we know how to find, not necessarily what might exist. Third, the object might be defunct. A probe launched millions of years ago might have exhausted its power source, suffered radiation damage, or simply completed its mission and shut down. We could be observing a derelict, technologically sophisticated but no longer functional, a ghost ship drifting through the void. Fourth, and this is the uncomfortable possibility, the object might be deliberately avoiding detection. If you're an advanced civilization sending probes to other star systems, you might program them to remain silent, to mimic natural objects, to blend in. Detection might trigger protocols, change trajectory, stop transmitting, activate camouflage. From the probe's perspective, being detected could compromise its mission or invite unwanted attention. So the silence tells us nothing conclusive. It's consistent with a natural comet. It's also consistent with a well-designed probe. We listen and we hear nothing, but nothing can mean many things. As of late 2025, 3i Atlas is leaving, moving outward, fading. The sun recedes behind it, becoming one star among many. Eventually it will exit our solar system entirely, crossing beyond the heliopause into true interstellar space. It will coast outward for millions of years, perhaps billions, until it encounters another star system. Or doesn't. Space is vast. The odds of another encounter within any meaningful time frame are vanishingly small. We had months to study 3i Atlas. Months. That's the window. That's all we get. Compare this to how we study objects in our own solar system. Comets in solar orbits return periodically. Halley's Comet comes back every 75 years. We've observed it multiple times throughout human history. We can track its evolution, watch how it changes over orbits, send spacecraft to intercept it. Asteroids remain in stable orbits for millions of years. We can study them continuously, plan missions, send probes, even land on their surfaces. Interstellar objects don't return. They're one-time events. We see them once, and then they're gone forever. All observations must happen during that brief window when they're close enough, bright enough, and positioned favorably for our instruments. And our instruments are limited. Ground-based telescopes contend with atmospheric distortion, weather, daylight. Space telescopes have limited field of view and must compete for observing time among thousands of other targets. Spectroscopy requires the object to be sufficiently bright. High-resolution imaging requires proximity and size. We did our best with 3i Atlas, observatory's worldwide coordinated efforts. Hubble captured images. James Webb, Space Telescope obtained spectra. Mars orbiters observed during the close approach. Ground-based facilities monitored continuously, tracking position and brightness. But there's so much we couldn't learn. We never resolved the nucleus. We never measured its exact shape or size. We never detected surface features or compositional variations across the surface. We never confirmed the internal structure or mass distribution. We never determined its rotation period with certainty or mapped its rotational pole orientation. All we have are measurements of the coma, the cloud, the exhaust. We're inferring the nature of the engine from the smoke it produces. And now it's leaving. The window is closing. Soon 3i Atlas will be too faint to observe, too distant for useful measurements, and then it will be gone. If we missed something, if there was a critical observation we should have made, a key measurement we failed to obtain, we won't get another chance. This is the urgency underlying all interstellar object research. You have one opportunity, one window, one chance to answer the question, what is this thing? And the window is always too short. There's a question that haunts the scientific community. It's called the Fermi paradox, named after a physicist who allegedly asked it during a casual lunch conversation in 1950. The question is deceptively simple. Where is everybody? The galaxy is old. Roughly 13.6 billion years old. Our sun is only about 4.6 billion years old, meaning there were billions of years before Earth even existed, during which other stars formed, other planets coalesced, other worlds potentially developed life. Some of those civilizations, if they exist, could be millions or billions of years more advanced than us. The galaxy is also large, approximately 100,000 light-years in diameter, containing between 100 and 400 billion stars. Even if only a tiny fraction of those stars have planets, and only a tiny fraction of those planets develop life, and only a tiny fraction of those develop intelligent life, and only a tiny fraction of those develop technological civilization, the numbers still suggest there should be many civilizations out there, possibly thousands, possibly millions. So where is everybody? Why haven't we detected them? Why haven't they contacted us? Why isn't the galaxy teeming with obvious signs of intelligence? Many solutions have been proposed. Perhaps intelligent life is extraordinarily rare. Perhaps civilizations destroy themselves before achieving interstellar capability. Perhaps advanced species deliberately avoid contact. Perhaps they exist, but in forms or dimensions we can't perceive. Perhaps we're in a cosmic zoo, observed but not contacted. Perhaps interstellar communication is impractical and civilizations remain isolated on their home worlds. Or perhaps they're here. Perhaps they've been watching us for a long time. Perhaps they send probes, quiet, patient, observing, to systems across the galaxy. Perhaps those probes are designed to look natural, to avoid detection, to blend in with the cosmic debris that fills space. Perhaps some of those probes occasionally pass through our solar system. Perhaps we've been seeing them for years and calling them asteroids or comets. Perhaps Oumuamua wasn't just an oddly shaped rock. Perhaps 2i Borisov wasn't just an unusually carbon dioxide-rich comet. Perhaps 3i Atlas is the latest in a long line of visitors that we've been misidentifying since the dawn of telescopic astronomy. This is speculation, obviously, pure speculation, but it's speculation rooted in probability. If interstellar probes exist, if any civilization anywhere has developed the technology and motivation to send automated spacecraft to other star systems, then statistically, some of those probes should arrive here eventually. The galaxy is old, time is deep. If probes were launched even occasionally over billions of years, the solar system would accumulate visitors. How many? That depends on assumptions. How many civilizations exist? How many send probes? How long do probes survive? What's the typical probe velocity? What's the density of probe trajectories intersecting our solar system? But even conservative estimates suggest we should encounter interstellar probes occasionally. Not constantly, not daily or yearly, but occasionally, perhaps once per century, perhaps once per decade. 3 interstellar objects in 8 years. Now here's where it gets strange again. We only started detecting interstellar objects recently. The technology didn't exist before. Survey telescopes capable of spotting small, fast-moving objects in deep space are new. Atlas, Pan-STARRS, ZTF. These are 21st century instruments. Before them, interstellar objects could have passed through the inner solar system undetected. Probably did pass through undetected. Dozens of them. Hundreds. We had no way of knowing, but now we can see them. And now that we're looking, we're finding them. 3 in 8 years. And one of them, the most recent, the largest, the most anomalous, raises questions we can't answer. Where is everybody? Maybe they're exactly where the Fermi paradox predicts. Maybe they're being cautious, sending probes instead of ships, observers instead of ambassadors, watching from a distance, waiting. Waiting for what? That's the question that keeps astronomers awake at night. Let's step back. Let's examine the natural explanations, because they deserve thorough consideration. Hypothesis 1, 3I Atlas, is an unusually large comet with a dense nucleus. This is the mainstream scientific position. Comets vary in composition and structure. We've observed comets with relatively high densities before, though not as extreme as 3I Atlas's implied density. Perhaps the object formed in a region of its parent star system where gravitational compression or collisional processes created a denser than typical nucleus. Perhaps it's not a pristine comet, but rather a fragment of a larger body, a piece broken off during a catastrophic collision billions of years ago, retaining a compacted, dense structure. The high mass could be explained by unusual composition. More rock, less ice, more metals, fewer volatiles. Formation in a metal-rich region of a protoplanetary disk could produce comets with substantially different density profiles than our solar system's comets. The carbon dioxide dominance, explained by formation in an extremely cold region far from the parent star, where water froze out first and carbon dioxide became the primary volatile in the remaining material. The forward jet, explained by surface topography, craters, fissures, or valleys that channel outgassing in specific directions. We know comets can have complex surface structures. Comet 67P Churyumov-Gerasimenko, visited by the Rosetta spacecraft, had dramatic topography including cliffs, boulders, and smooth plains. 3I Atlas could have similar features. The trajectory, coincidence, low probability events happen. Random chance sometimes produces patterns that look meaningful, but are actually just statistical fluctuations. This hypothesis is plausible. It doesn't require exotic physics or speculative technology. It's consistent with known cometary science, though it pushes the boundaries of that science in multiple ways simultaneously. Hypothesis 2. 3I Atlas is a captured object, not truly interstellar. Perhaps 3I Atlas originated in our solar system long ago and was ejected by gravitational interactions with Jupiter or another giant planet. It spent millions of years in a highly elliptical orbit, far beyond the planets, and only recently returned on a trajectory that appears hyperbolic due to measurement uncertainties or perturbations. This would explain why its characteristics seem unusual for an interstellar object. Because it isn't truly interstellar, it's a native object masquerading as a visitor. However, orbital analysis strongly suggests a hyperbolic trajectory. The object's velocity and path are consistent with interstellar origin, not solar system capture. This hypothesis has been considered and generally rejected based on the data, though some uncertainty always remains. Hypothesis 3. The Atlas represents a population of large interstellar comets we simply haven't detected before. Perhaps the galaxy is full of objects like 3I Atlas, massive, dense interstellar comets, and we've only just now developed the technology to spot them. The first two interstellar objects, Oumuamua and 2I Borisov, were smaller and therefore more common, detected first only because they happened to pass closer to Earth or at more favourable angles. 3I Atlas represents the rare but natural end of the size distribution, the big ones. They're uncommon, but they exist. We just hadn't seen one until now. This is possible. Detection bias is real. We see what our instruments are capable of seeing, and our instruments have limitations. But this hypothesis has a problem. If large interstellar comets like 3I Atlas exist in significant numbers, we should have detected them before. Their size makes them brighter and easier to spot. The fact that we detected two smaller objects before one large object suggests the size distribution favours smaller objects, which is consistent with normal cometary populations. Finding the largest object third is backwards. It's like surveying trees in a forest and finding saplings before you find redwoods. Possible, but statistically peculiar. Hypothesis 4. 3I Atlas is an interstellar interloper of a type we don't yet understand. Natural, but exotic. Perhaps interstellar space contains objects formed under conditions we haven't imagined. Perhaps there are processes occurring in molecular clouds, in the outskirts of stellar systems, in the depths between stars that create objects with properties unlike anything in our solar system. Perhaps 3I Atlas is natural, but represents an entirely new category of interstellar object, something neither comet nor asteroid but a third type, forged by exotic astrophysical processes we haven't discovered yet. This hypothesis is appealing because it explains the anomalies without invoking artificial origin, but it's also frustrating because it's essentially unfalsifiable. We don't know what it is, but it's natural, is scientifically valid, but unsatisfying. All of these hypotheses are possible, all have strengths and weaknesses, none are perfect. Which brings us back to the hypothesis nobody wants to say out loud. Let's say it clearly. Some researchers have seriously considered whether 3I Atlas could be an artifact of extraterrestrial technology, not as a conclusion, not as a definitive claim, but as a hypothesis worth investigating. The reasoning goes like this. If we accept that technological civilizations exist elsewhere in the galaxy, a premise supported by statistical arguments about the number of potentially habitable worlds, then it follows that some of those civilizations may have developed interstellar probe technology. Not faster than light travel, not warp drives or hyperspace, but simple, robust, automated spacecraft capable of crossing the vast distances between stars over long timescales. Such probes would need several characteristics. Durability. They must survive millions of years in interstellar space, enduring cosmic radiation, micrometeorite impacts, and the degrading effects of time. Self-sufficiency. They must operate without external support, relying on onboard power systems, perhaps radioisotope generators, fusion reactors, or something we haven't conceived. Autonomy. They must make decisions independently, unable to communicate with their creators across light years of distance with any meaningful feedback loop. Stealth. They might be designed to avoid detection, either for scientific non-interference or strategic security. Announcing your presence in an unknown star system could be unwise. What would such a probe look like? Probably not a sleek spacecraft with lights and antenna. More likely, it would be utilitarian, heavily shielded, possibly disguised. And the best disguise? Look like something natural. Look like a comet. A comet is expected. A comet is ignored after initial classification. A comet doesn't trigger alarms or intense scrutiny. A comet is the perfect cover for a probe designed to observe without being observed. You would construct a dense metallic or ceramic core housing instruments, computers, power systems, and data storage. You would coat this core in ice, water, carbon dioxide, whatever was readily available in your stellar system. The ice provides radiation shielding and thermal insulation. As the probe approaches a star, the ice sublimates naturally, creating a coma that further obscures the core and makes the object appear cometary. You would engineer vents or thrusters using the sublimating ice as propellant, allowing small trajectory corrections while maintaining the appearance of natural outgassing. You would design the object's trajectory to pass through the target system's habitable zone near planets of interest, maximizing observational opportunities. You would make it heavy enough that natural outgassing doesn't significantly perturb its trajectory, avoiding the non-gravitational acceleration that would invite detailed analysis. You would equip it with passive sensors, cameras, spectrometers, magnetometers, radiation detectors. No active transmissions, no radar or LiDAR pings. Just watch, record, store data. And if detected, you would remain silent. You would mimic natural behavior. You would rely on the assumption that the inhabitants of the system would classify you as a comet and move on. This is what a realistic interstellar probe might look like. Not a science fiction spacecraft, not something obviously artificial, but something subtle, something patient, something designed to blend in, something exactly like 3i Atlas. This isn't the first time this hypothesis has been seriously considered. When Oumuamua was discovered in 2017, its unusual characteristics prompted researchers to investigate whether it might be artificial. Its extreme elongation, its lack of visible coma despite non-gravitational acceleration, its tumbling rotation, all suggested something atypical. Radio telescopes, including the Green Bank telescope, observed Oumuamua for signs of artificial transmission. None were found. But the fact that such observations were conducted at all indicates the scientific community takes the possibility seriously. Papers were published examining Oumuamua through the lens of various hypotheses, including technological origin. The scientific method doesn't forbid unconventional ideas. It requires they be tested rigorously. So researchers tested the idea. They looked for evidence of artificiality. They found none that was conclusive, though the anomalies remained unexplained for years. Eventually, natural explanations were proposed: hydrogen icebergs, nitrogen ice fragments, cometary fragments with unusual properties. These explanations remained debated, but they provided plausible natural alternatives to the technological hypothesis. The precedent was set. When interstellar objects exhibit significant anomalies, investigating all possibilities, including artificial origin, is scientifically appropriate. Speculation becomes science when subjected to observation, analysis, and peer review. 3i Atlas follows this precedent. Researchers have published papers noting the object's unusual characteristics. Some have explicitly discussed the possibility of technological origin, not as certainty, but as a hypothesis requiring investigation. And that investigation is ongoing. Data continues to be analyzed, models continue to be refined, observations continue to be reviewed. But time is running out. The object is fading. Soon it will be beyond detection range, and we still don't have answers. Suppose, just for a moment, that 3i Atlas is artificial. Suppose it's a probe from another civilization. What would that mean? First, it means we're not alone. Somewhere out there, intelligent beings exist, or existed, capable of building interstellar probes. This alone would be the most significant discovery in human history. It would fundamentally alter our understanding of our place in the universe. We would no longer be wondering if intelligence exists elsewhere. We would know. Second, it means interstellar travel is possible. Not easy, probably. Not trivial, but achievable. A civilization somewhere figured out how to cross the vast distances between stars, even if only through automated probes. This provides hope that humanity too might someday reach beyond our solar system. It establishes a proof of concept. Third, it means the galaxy might be monitored. If one civilization sends probes, others probably do too. The solar system might receive regular visits, quiet observations from passing automated spacecraft, cataloguing our world, watching our development. We might be less alone than we think. We might be watched. Fourth, and perhaps most unsettling, it means those probes are designed to avoid detection. 3i Atlas, if artificial, passed through our solar system without making any obvious attempts at communication. No radio broadcasts, no flashing lights, no attempts at contact. It came, it observed, presumably, and it's leaving. Why? Why observe, but not communicate? Perhaps communication is deemed too risky. Perhaps revealing the probe compromises its mission. Perhaps the civilization that built it follows a principle of non-interference, watching but not interacting, studying but not disturbing. Or perhaps communication requires us to reach a certain level of development first. Perhaps there are protocols, rules, thresholds. Perhaps we're being evaluated. Perhaps contact comes later, after we prove ourselves capable or worthy already. Or perhaps the probe is ancient, its builders long extinct. Perhaps we're seeing the ghosts of dead civilizations, their automated messengers still carrying out programmed missions millions of years after their creators vanished. Perhaps the galaxy is full of such relics, orphaned probes drifting forever, observing worlds on behalf of species that no longer exist. Each possibility has profound implications. None are comforting. All require us to reevaluate our assumptions about the galaxy and our future within it. But these implications only matter if the premise is true. If 3i Atlas is artificial, and we don't know that, we can't know that, not with current data. The Vera C. Rubin Observatory, currently under construction in Chile, will begin operations soon. This observatory is designed to conduct the Legacy Survey of Space and Time, LSST, a comprehensive survey of the entire visible sky every few nights. It will detect faint, fast-moving objects with unprecedented sensitivity. When LSST comes online, the detection rate of interstellar objects will increase dramatically. Instead of 3 per decade, we might detect dozens per year, perhaps hundreds. The census of interstellar visitors will grow from a handful to a robust population. This matters because statistics require sample size. 3 objects aren't enough to draw meaningful conclusions about the nature of interstellar populations. Anomalies can be flukes. But with hundreds of detections, patterns will emerge. We'll learn the typical size distribution, composition range, trajectory characteristics, and behavioral properties of interstellar objects. And if 3i Atlas is truly an outlier, if large, massive, unusually composed objects remain rare even in a much larger sample, then its anomalous nature becomes more significant. If it's not part of the natural population, then what is it? Alternatively, if dozens of 3i Atlas-like objects are detected, the technological hypothesis weakens. One unusual object might be artificial. Dozens suggest a natural population we simply hadn't observed before. So, the future of this question lies in detection. More data, more observations, more objects to compare and analyze. But there's also the possibility of direct investigation. Spacecraft designed to intercept and study interstellar objects are being proposed. Small, fast probes that could launch on short notice when an interstellar visitor is detected, accelerate to intercept and conduct close-range observations. Such missions are technically challenging. Interstellar objects move fast and are detected late. You have a narrow window to plan, build, launch, and intercept. But it's not impossible. With sufficient funding and pre-positioned hardware, we could do it. Imagine a spacecraft arriving at 3i Atlas, or the next interstellar visitor. Imagine high-resolution imaging of the nucleus. Imagine surface mapping, compositional analysis, mass measurement. Imagine actually seeing what these objects are made of beneath the coma. That data would answer the question, not through inference or modeling or statistical analysis, but through direct observation. We would know. But such missions require decades of planning and billions in funding, and even then, you have to get lucky. An interstellar object has to arrive at a convenient time, on a convenient trajectory, when your spacecraft is ready to launch. For now, we work with telescopes. We observe from a distance. We collect photons and spectra and try to reconstruct reality from scattered clues. And we wait for the next visitor, wondering what it will show us, wondering if it will answer the questions 3i Atlas raised, wondering if we're ready for those answers. There's a weight to this uncertainty, a heaviness that settles over anyone who spends too long thinking about it. Because here's the truth, we might have just witnessed one of the most significant moments in human history, and we might have missed it. If 3i Atlas was artificial, if it was a probe sent by intelligent beings from another world, then it passed through our solar system and we barely noticed. We saw it, we observed it, we collected data, but we didn't recognize it for what it was. We catalogued it as a comet and moved on. And now it's leaving, fading into the darkness, carrying whatever information it gathered back into the void. Or perhaps not back. Perhaps it's just drifting, mission complete, heading toward no destination, its data stored in memory banks that will never be retrieved because the civilization that sent it is gone. Either way, the moment has passed. The opportunity is slipping away. And we're left with questions we can't answer and suspicions we can't confirm. This is the weight of cosmic uncertainty. The knowledge that we're surrounded by mysteries we lack the tools to solve, that the universe is full of phenomena we can observe but not comprehend, that some questions might remain forever unanswered, not because the answers don't exist, but because we asked too late or looked too briefly or didn't quite have the technology to see what was right in front of us. It's humbling, profoundly humbling. We are so small, our technology is so limited, our understanding is so incomplete, and the universe is so vast and strange and full of possibilities that exceed our imagination. 3i Atlas reminds us of this. Whether it's natural or artificial, it represents something beyond our full comprehension. It came from another stellar system, a place we will likely never visit, formed under conditions we can only estimate, carrying information about worlds we will never see, and we watched it pass, for a few months, with instruments barely capable of resolving its coma, let alone its nucleus. We gathered what data we could. We asked what questions we thought to ask. We did our best. But was our best enough? Did we miss something critical? Did we fail to make the observation that would have answered everything? We'll never know. Not with 3i Atlas. It's gone now for all practical purposes. Fading, leaving, becoming once again just another faint point of light among trillions, until even that light becomes too dim to see. And we're left here, on our pale blue dot, looking up, wondering what we saw, wondering what we missed, wondering what's out there in the darkness, watching us in return. So, where does this leave us? With uncertainty, with questions, with the knowledge that we live in a universe stranger and more complex than we often acknowledge. 3i Atlas might be an unusually large and dense comet, a natural object formed under exotic conditions in an alien star system. It might be a fragment of a shattered world, a piece of a planet torn apart by tidal forces or catastrophic collision. It might represent a population of interstellar objects we simply haven't sampled adequately yet. Or it might be something else, something built, something sent, something watching. We don't know. And that's okay. Not knowing is where science begins. Uncertainty is the foundation upon which understanding is built. Every major discovery in history started with someone looking at something familiar and asking, but what if it's not what we think it is? What if the Earth isn't the center of the universe? What if species change over time? What if space and time are connected? What if the universe is expanding? What if particles can be in two places at once? These questions seemed absurd when first asked. They violated common sense and challenged established understanding. But people asked them anyway. They investigated, they tested, they followed the evidence wherever it led, even when it led to uncomfortable or revolutionary conclusions. 3i Atlas deserves the same approach. We should investigate all hypotheses, natural and artificial, with equal rigor. We should collect data, build models, test predictions, and let the evidence guide our conclusions. We should remain open to unconventional explanations while demanding extraordinary evidence for extraordinary claims. And we should stay curious about what else might be out there,